All right. So QA. All right. So you guys all know about QA because you're in the clinic and you're probably getting some practice in QA, and that's great, and those are the practical aspects of QA. You might be learning some of the theoretical aspects. So we're gonna talk about why you do QA, where the tests come from, just so you folks know if you have a question where to go to, and where the guidance documents are. And we'll talk about the test too in some detail as well. This chart. Okay, so why do we perform QA? And QA is very broad, right? And in the broadest sense, QA means probably a quality management program for a department. Okay, so that's the broadest sense of QA, a quality management program. And so that permeates everything we do. That permeates the QA of our charts. That permeates the QA of the equipment. The QA of policies and procedures, and what QA aspects we include in policies and procedures. It includes continuing QA, in other words, improvement of QA. And then it includes all the equipment that we look at. We look at equipment QA such as electrometer QA, chamber QA, all the instruments you use, map check QA, daily dose checker QA, and then the Accelerator QA, CT Sim QA, HDR QA, right? Stereotactic radiosurgery program QA. And so it includes a vast majority of everything we get involved with. And depending on what clinic you go to, this will be either very generalized, the QA program will be very generalized, or it'll be specific to each machine, and there won't be too many, they won't be tied into each other. Okay, so the QA program should start as a general theme and a general thinking in terms of QA, and then kind of drill down to the particular machines. Or it could be machine by machine, and the philosophy of the QA could be different, which is not a good arrangement. It's better to kind of come up with a philosophy for your entire QA program. And what I mean by philosophy is who's involved in it, how often do you need to review it, do you need to have meetings to talk about continuing QA. So who do you think is responsible for the QA program in a department?
Physicists.
The medical physicists. We are the ones that are responsible. Of course, we can't do it alone, because everything, if we bring a QA program to the clinic, we want people to do what we want them to do, right? So you need to bring everybody into the fold and talk about what your QA program involves. And that includes the department manager, obviously the medical director. And all these people have to be behind your QA program. But really the medical physicists, we're seeing more and more of this because of the errors that have come up in the news, and because we're working harder at minimizing errors these days. So it argues for a larger encompassing QA program. Okay? And therefore, our role over the last few years has changed significantly because we're more involved in the QA program itself and less involved in just like, okay, I'm going to QA the HDR unit, I'm going to go QA the Linac. We need to bring it all together as an entire program. And so like I said, we're being more involved these days, but we don't have the training to do it. Okay? And so there are several courses that you can go out and take, training in radiation safety and QA. One of my colleagues is going to minimizing patient error meeting. So he's going to go there, he's going to learn about it, bring it to us. So this is our challenge right now. We're really busy in the clinic, and things keep coming up. Like new technology comes up, and now this QA involvement, how we have to be involved in the QA process. So our role is changing over time, and it's actually making our role more of a challenge because we have to learn a lot more these days than we did before. Okay, so reasons to perform QA. Regulations come from the states. Okay, and regulations come from the states. Now, those regulations have to do with mostly X-ray producing machines. Okay, so the states regulate X-ray producing machines such as linear accelerators, produce X-rays, X-ray units, CT scanners. So the regulations that regulate those machines come from the states. The National Regulatory Commission, these guys are feds. Okay, so these are federales. They come from the FDA. They come from they're federal. They're not state regulated, and they don't regulate radiation-producing machines. They regulate radionuclides. Okay. Now, there's a difference between an agreement state and a non-agreement state. Have you guys heard those terms? Agreement state, non-agreement state? An agreement state is a state who takes on the responsibility of regulating radionuclides. Okay, so these guys, radionuclides only. Only. Okay. So an agreement state is a state that takes on the responsibility of both radiation-producing equipment and radionuclides. Illinois is such a state. So the regulations in Illinois will regulate both radionuclides and radiation-producing machines, and our regulations, we have to conform with what the state, all the regulations of the state. We don't go to the NRC to look at regulations. Okay, but our IEMA, our Illinois Emergency Management Agency, goes to NRC and says, we agree with everything the NRC, all the NRC regulations, but we might have our own little things going on. In other words, they might be more stringent on certain areas. Not less stringent, they can only be more stringent, okay? So, so most of this talk today, most of the QA talk will pertain to radiation-producing machines and radiation equipment. I'm not going to go into brachytherapy or radionuclides too much. Okay. So does that make sense, right? An agreement state, if you're in an agreement state, you only need to go to the state regulations. You don't need to go to NRC. If you're a non-agreement state, then you need to go to NRC for your radionuclide stuff, and then you have to go to the state regulations for your X-ray producing materials. That's just a simple, it gets a little more complicated, but that's just a basic summary. Have you guys gone to the IEMA website? Take a look, kind of poke around, see what they're, okay. So this is where the IEMA website is. And this, I think this is just part 360, but you could go up one level to get to everything else. State regulations are very detailed about radionuclide QA. There's a lot more regulation for radionuclides than there is for X-ray producing machines. For example, for many years, there was a condition that if you had a cobalt-60 unit, right, it's an external heat machine. So that falls under all the radionuclide laws. Now, if there was a misadministration with this machine, you had to report it right away, and then there was misadministration guidelines, such as, I can't remember what they are, but something like, if the misadministration involved a 20% overdose within 1 week, then it was a reportable event, and this is just an example. But if it was like 5% within a week, it was a reportable event. So there were different tiers for, those aren't the regs, I'm just giving you an example. There were different tiers based on what the events were. And you'd expect that those regulations exist for linear accelerators as well, because there's more Linacs out there, you treat more patients with them. They were never there. Okay. So that's just an example of how less stringent the state is with radiation-producing machines compared to radionuclide-producing machines. This reportable and recordable event is only now they're starting to talk about it for linear accelerators. And there's a proposed law that might come into effect pretty soon for linear accelerators, but it's still not there. Okay, so that's just an example. So if you look at the area of regulations of radionuclides, they're much larger than the area of radiation-producing machines, such as like accelerators, X-ray units, mammography units, etc. And by the way, I just mentioned mammography units. Mammography units fall under the FDA. So the FDA controls the regulations of mammography units under the MQSA Act. There's another set of regulations for mammography machines. So they have their own thing. So let's see, Illinois Emergency Management Agency requires a few QA tiers. Here's another example. They only require, this is for linear accelerators, they only require a few QA tests on a monthly basis and a few on a yearly basis. The yearly requirement is that you send TLDs to independent lab every 2 years. So that's all you need to do. So the IEMA require, the few QA tests are, let's see, do I have them here? I think I have them on the next slide. They only require that you do light versus radiation field check on a monthly basis, that you do outputs on a monthly basis, and then that you send your TLDs or cells out on a yearly basis. That's it. So it's not a lot. Considering how complicated linear accelerators are, we know we do a lot more than that, right? But there's no agency that makes us do this. We do this because it's just standard practice. TG40 is out there, TG142 is out there, that gives us guidelines for doing that. And we do it just because We want to deliver safe radiation to the patient. Okay. So the main reason to do QA is to deliver accurate treatments to your clinic patients, and following standard of care based on guidance documents also keeps your clinic from appearing negligent in case a lawsuit is brought forth. All right, so TG40. TG40 is the initial original QA document published in 1994. It's an early guidance document that covers many aspects of write-on QA. Okay, it's not just Linac Accelerator, it covers a lot of things. HDR, covers CT scanners, etc. Okay, so it covers policies and procedures, QA of mobile machine Linux. It covers treatment planning systems, brachytherapy sources, and simulators. Okay, it covers dose calculations, treatment delivery, remote afterloaders, measurement equipment, and chart checking and film review. So it covers all this stuff. Right? It's a good guidance document to give you an idea of what you should be doing in the clinic. If you walk into a new clinic and a new job, you should go in there and just look at TG40 and review what they're doing in the clinic and how it compares to TG40. And it'll give you a good idea whether they're doing a good job in terms of QA. TG40 test frequencies. So their test frequencies are classified into different categories: daily, monthly, and yearly. And at Evanston Hospital, we also do quarterly. That's just our thing. So a daily test consists of, why do you do daily tests? Why do you need to do a test on a daily basis? Well, that's probably because the things that you're testing on a daily basis are items or parameters that will fluctuate more often than other things that you don't do on a daily test, such as, or also things that will seriously affect the patient's treatment. Okay, that you want to make sure you check every day. So those things are lasers, because lasers are still being used to set up patients, and lasers do drift. We know that lasers drift. Okay, and lasers can be bumped. ODI, which some places still rely on ODI. That's why they should, as a double check, or maybe even as a patient. People set up patients with ODIs. Okay, so do you think an ODI drifts a lot? It probably drifts less than a laser, at least on varying machines. I've never seen an ODI be off. So it's a light source, and the light source doesn't move. The light source shines through this really thin screen. The screen is an etched piece of metal that really doesn't change. So it really doesn't change much, but it can affect patients' treatment. It can affect patients' treatments because well, if it doesn't change much, it's not going to affect patients' treatments. But since you use it so often, you want to check it. Light field size. This is important too, because they'll shine a light field on a patient and they'll verify where the light field's going. If the light field's not going in the right place, it might not tell them that. It'll look like they're irradiating in a place they don't want to irradiate. So you want to check light field size. And this, I did see this change. So the jaws can get miscalibrated. MLCs not so much, but the jaws can get miscalibrated. They have to check that. There was actually a recent customer technical bulletin from Varian that came out that says there was a site where the jaws miscalibrated on their own. There was some electronic fluctuation, and the field size was incorrect. And there was a big uproar about it in the community because Varian's customer technical bulletin recommended that you check the field size for every field, which means that the therapist needs to go in the room, look at the field size, make sure it's right somehow make sure it's right. I'm not sure how they're going to do that. And leave the room and treat the patient. Then go in again and check the light field. So this caused a big uproar in the bulletin, in the medical physics listservs about how it's unreasonable to expect us to do that. We check the light field size every morning. I think that's good enough. Output constancy. Does the output of the machine change? Very rarely. When I do TG51 every year, I rarely have to tweak it. Okay. So at least for a Varian machine. Of course, that depends on the machine. Some machines might fluctuate more than others. An older machine, so it's a good idea to do output constancy for all machines. Now, what about some places will do output constancy on photons only, and they'll only do output constancy on electrons if they're treating with electrons. In my opinion, that's not the best practice because doing output constancy, you've got your equipment set up, you might as well do all the energies, and that way you could track your constancy of your electron energies, because there could be energies that have fluctuated more than others. So if you start a patient on an electron energy and you haven't monitored it in the past, you don't know what kind of record it has. So it's a good idea to just do all the energies. It doesn't take that long. Especially today with the daily dose checkers, you just put it down on the machine, and then you can do everything from outside the machine. You don't need to go in the room. So those are dailies. The other thing that they do on a daily, I think I've got another slide I'll talk about it. And then monthly tests. So those are for systems that may change considerably within a year, but not from day to day. So you do tests, that monthly tests, even though you're looking at things that might change within 1 year. You wouldn't do a monthly test on something that's going to change during the month because it's too late. If you're doing it on a monthly basis, you're not going to catch it. Right? You're looking for things that are going to fluctuate within 1 year. If they're going to fluctuate within a month, you're going to do a daily test on it, okay, so you can catch it. Okay, and then yearly tests, those that include systems that are not expected to change much over 1 year. Tolerance and constancy values. So tolerance values are set such that the overall dosimetric accuracy is within 5%. That's our goal. Our goal in radiation therapy is to deliver treatments so that the dosimetric and positional accuracy and spatial setup uncertainty is within plus or minus 5 millimeters. So this is what we're looking for, 5% and 5 millimeters. We want to be able to deliver the dose to the patient within 5% of the prescription, the doctor's prescription, and we want to be able to set up the patient within plus or minus 5 millimeters. That's our goal. This seems big, doesn't it? 5 millimeters? It seems big, but if you add up all the errors, that's what we're looking at. This is the sum over all possible errors. Where do these numbers come from? ICIU report number 24. Okay, that was a recommendation. It's been out for a while. Okay, and then, so those are tolerance values. So when we're looking at our spreadsheets, we say, well, we want the output to be within 2%. That's what we call a tolerance value. Constancy values ensure systems perform within specs between testing periods. So that's constancy. Remember the difference between tolerance and constancy. You can have tolerance values within your constancy. So what are the daily tests? Now let's get into a little more detail about the actual test itself. Output, daily dose checker. You guys have seen daily dose checkers, right? Pretty simple devices. This is an example of one that has, this is an RBA. It's an older unit. And here's the plate. You put the plate under the beam, center it on here. There's 1, 2, 3, 4, 5 chambers on there. Why are there 5 chambers? Because the center chamber is used to calculate the dose. And the chambers on the sides are used to calculate the flatness and symmetry of the beam. More really symmetry, not as much flatness. Flatness isn't going to change that much. Symmetry tends to change more than flatness. And then this device is either you can read out the numbers here, or you can connect it to a computer software that reads them out. And it stores them every day. Okay, so the therapists come in and they set that up. The usual alert level for these are 3%. And that's the alert level, which means that if the dose or symmetry is above 3%, they have to let physics know. If it's under 3%, they don't have to let anyone know. They can just keep going. And then the no treat level is 5%. No treat meaning you can't treat a patient until physics fixes it. And that's 5%. That's pretty typical across the board. I mean, we've tried this at 2%, and we tend to get a lot of calls. It's not necessary. 3% is fine. These devices they're not as accurate as an ionization chamber that we use. And also, the therapists are moving very quickly in the morning, so their setup might not be ideal. So that's why 3% is there. And 3% is fine. I mean, we don't expect the outputs to vary. They also check audiovisual, make sure they can see the patient, make sure they can hear the patient in case the patient screams. So this is actually a state requirement. You have to be able to visualize the patient. Say you've got one camera looking at the patient, and the therapist comes in the morning, the camera's dead. They call you up, they get you out of bed, because they're really early in the morning doing warm-ups. They say the camera's out. What do you think you can do about that? What's the possible solution?
You would need to call the engineer, right?
Yeah. First of all, you can't treat. Okay, so you need to know that it's a regulation that you can't treat. So this is where you guys need to know the line where you can say treat or don't treat, okay? And that can get us into trouble sometimes, because if you don't know that line, you say don't treat, and they can actually treat, and you can get into a little bit of trouble. So you need to know where the line is where you can say don't treat. Okay, so if the camera's out, they're not allowed to treat. Okay, now some places have these mirrors where they can look through the window of the door and see the mirror, and it's pretty clear that they can see the patient. That's a possibility, as long as the mirror is very clear. So you have to be able to have visual connection with the patient. So if the camera doesn't work, yeah, you have them call biomedical engineering or facilities or something to get it done. But that's a definite no treatment. Laser alignment, again, if it's 5%, you have the authority to say do not treat. Okay. You might have to go through a troubleshooting process with them over the phone. It's always harder over the phone, of course. Another possibility is that this daily dose checker is not working that way. So the first thing I do when they call me about that, I say, well, how were the outputs in the last week? And they'll look at their outputs and they'll say, they're fine, they're right on. So, well, why don't you use a MOSFET if they have a MOSFET or a TLD, not a TLD system, but some kind of direct readout system where they can put a MOSFET on, shoot a 10 by 10, and get a dose reading from that. I said, try a MOSFET. So that's another possibility. And at times when there was no MOSFET, this thing was broken, but the outputs were fine, I actually I gave them the go-ahead to treat, and then I'd come in and just double-check the dose checker. Okay. Just because I know that the linear accelerator, if it's a Linac that's really old and I don't trust it, I wouldn't say go ahead and treat. But if I know the record of this linear accelerator and the daily dose checker is down for one day, I might give the go ahead to treat until I come in, and then I'll check it out when I get it. Light field size with laser alignment screw. Okay, so you could check the light field size in different ways. Sometimes these daily dose checkers have a square on it, okay, so they could just compare the field size on the square. Or the laser alignment tool, you know that little tool that has leveling screws on it, and you can align those. You can use that. There's a 10 by 10 square on there. And then ODI, you bring the laser plate up to 100, and then verify the SSD. It should be 100. They don't need to check more than 100 on a daily basis. 100 is fine. And then they also check the gas pressure. So you guys remember what the sulfur hexafluoride gas does? It's a dielectric. So they make sure the gas pressure is up to where it has to be. And do you know what that pressure is for a variant? It's 32 psi. Cooling water temperature should be around 40 degrees. They check that too. Okay, so they check the gauges as well. Monthly tests. So what do we do on a monthly test? Monthly tests are done by physicists, not therapists. And so let's go down the list here. We verify that the calibration of the Linac dosimetry is consistent from month to month. Again, you're going to see this consistent. We're not doing a TG51 every month, although some centers do. I know that some centers will set up this little water tank and do the TG51 every month. You don't need to do that, because you're just checking for consistency. You just verify that the machine hasn't changed from what you expect it to change. Right? And then, so setup. You can use a plastic phantom. Again, it's for consistency. SAD or SSD, whatever you think is more practical. You can use the same depth for 6 and 10 photons. Who's I working with that said they use different depths for 6 and 10? You don't really need to. You're just checking consistency. That depth should probably be, I use 5 cm, a 5 cm depth because it's greater than Dmax. I don't want to be within Dmax because if I am, then I have to change the depth for the different machines. So I use 5 cm, and then electron depth, choose a depth close to Dmax for good signal strength. Okay. So for electrons, I will have different depths, like the 6 MeV has a Dmax of like 1.2. But then the 9s, 12s, the other ones, they're above 2. So I'll usually use a thin piece for 6 to get a good signal, and then I'll go in and change it up to 2 cm for all the others. Okay. Then verify the dose rate, MU1 and MU2 agreement. So as you're doing this, make sure that MU1 and MU2 agree. If they start to disagree, it's a calibration issue. You need to go in there and calibrate. If they start to disagree by more than 10%, the therapists are going to start getting interlocks. Okay, so you don't want that to happen. Dose cal should not drift unless there's a problem. Okay, so the calibration is usually pretty consistent. Energy checks are also done on a monthly basis. I do energy checks on a monthly basis. It doesn't take that much longer. You just put some more plastic on there and compare. What you're doing is if this is a PDD curve, what you're doing is at first here's 5 cm, and then here's okay, so you get a certain signal at 5 cm, and then you'll slap on another 5 cm out here, and you get another signal here. And to do an energy check, you're taking the ratio of this over this. Now, if the energy of that beam changes for some reason, it'll change your PDD, right? It'll be either more penetrating or less penetrating, and so the ratio of these two numbers will change. Okay, so basically what you're checking. It's not a very sensitive test. You're just checking for source error. Always remember to correct for air density for your chambers. Check leakage within your measurement system. Okay. How do you do that? How do you check leakage? Hook everything up, right? Hook up your chamber, your electrometer, make sure it's all hooked up, make sure your bias is on, and then go to the most sensitive current scale. Turn it on, look at your current leakage. What should your leakage be? Okay, remember? Try to keep the number in your mind because it's something you're going to check every time you do an output. So my rule of thumb is less than 0.04 picoamps. Okay. And it actually should be better than that for a good system, like for a farmer chamber and a good electrometer. I believe the spec is like 0.01, but I'm happy if I see less than 0.04 picoamps in my system. Okay. And I often see that higher, and I often see it fluctuate. So say you start to see a higher current, what should you do? What's your troubleshoot? What do you think your troubleshooting steps? Well, there's three pieces that you've got. You've got an electrometer, you've got a cable, and you have a chamber. So what I would do is I unhook everything, take the chamber, plug it straight into the electrometer, straight out without the cable, and then check my leakage. If my leakage drops, then I know it's my Triax cable. Okay? So I'll unplug my chamber, plug my Triax in, and I'll probably see if I have leakage issue. Or not plug anything in and see if I have leakage. If I have leakage, then it's something in the electrometer. It's just troubleshooting steps. If you want, you can plot the results that you get on a monthly basis. So outputs, you can plot your outputs just to look for trends. There typically isn't too many trends. There usually doesn't really follow a trend. It's usually pretty random. But you can track it in case you're having issues. And then, of course, verify setup if things aren't looking good. And then I have a star here. It could be quarterly. I guess I have this. This one could be done on a quarterly basis. And then, why do we go quarterly at Evanston? We went quarterly because there's just so many tests to do. And I know that a lot of the tests over the years, a lot of these parameters don't change over the years. They don't change over an entire year. So the question is, why am I doing this on a monthly basis if I don't expect it to change every year? So the ones I don't expect to change, I'll put in the quarterly QA. Okay. And so that lightens up my monthly QA load a little bit. And these days with TG 142, monthly QA is extremely time consuming. Okay, monthly test mechanical. So those are some of the output tests. And this one's mechanical. Radiation versus light field tests. You guys have all done that. Position of jaws, target and mirror, verified digital readouts also. Light field alignment test. We don't do this one too often. I like to do this test. And this test here is done. For the light field alignment test, what you're doing is you're verifying that your mirror and your light, as you rotate your collimator, your point source where the light's coming from is aligned to the axis of the rotation of the collimator. And you do that. Here's the experimental setup. So this is the gantry, and the light source is somewhere up here. Shines down. Okay, and then here's the couch. I'll put a credit card on the end of the couch right here, and I'll put a piece of paper down here, and I'll look at the shadow with the collimator, a 90-degree collimator. 90-degree collimator. I'll look at the shadow of this credit card, and then I'll draw the edges of the credit card, and then I'll rotate the collimator to 270 degrees, and then I'll see where that shadow ends up relative to my original marks. Okay. And if there's a shift, it's telling me that as the collimator is turning, that light source is not aligned with the axis of rotation. Okay, so that's a lot of people don't do this, but this you should probably do before you do your light versus radiation field check, because they're not going to match if this doesn't work out. On newer machines, this is usually this test passes easily. On older ones, it doesn't pass so easily. Okay, target and mirror, verify the light field line. Okay. All right, and then flatness and symmetry. So the equations for flatness, there are different equations for flatness and symmetry. As you know, I go to TG45, and here's the equation for flatness, very simple one, right here. So what's flatness? Flatness is given by reading m minus reading little m divided by reading big M plus reading big M, where m and little m are the maximum and minimum dose values in the central 80% of the profile. Manufacturer's symmetry is open. So this equation can change from manufacturer to manufacturer. But basically, what it means is, here's your profile. For flatness, you're looking at if this is a 10 by 10, you're looking at 4 cm from this side and 4 cm from that side, and you're looking at the maximum minimum doses within that area. And so maximum tend to be, if usually there's some horns, so the maximum tend to be up here, and the minimum is down here at the central axis. So you subtract that minus that over the sum of that times 100, and that's a percentage. Okay. Okay, and then the symmetry is often defined as the maximum percentage deviation of the left side versus the right side. Okay, so for flatness, you're not looking at left and right, you're looking at the entire thing, and you're looking at the maximum point from here to here, wherever that may be. Could be on the left, could be on the right. With symmetry, you're comparing this point to this point. So you're comparing left and right. Okay. So how can the flatness symmetry be affected? That can be affected by the position of the target, it's not going into place, or the foil position for electrons, not properly positioned. And your bending magnetic currents can affect the symmetry. Okay, so if there's an issue with those things, those are usually the culprits. Most common is this one. Okay. Has anyone done any beam steering? Here, haven't seen any beam steering? Okay, so if you do have an issue like that, you need to call the manufacturer in and have them come steer the beam. And usually you'll use something where you can do a direct readout of the symmetry. Direct readout meaning you don't want to set up a water tank and run your chain back and forth. It just takes too long. So direct readout could be, you can use a map check, or you can use a profile, or something that's going to give you an instant symmetry, because then the engineer can tweak and watch what happens as they tweak dynamically. And then integrity checks, wedges, couch, applicators, gradicule. So what do you check on wedges? Integrity checks. What's a good integrity check? Shake it, right? Yeah, the Etch-a-Sketch test. Shake it. Make sure it's that everything's screwed on tight. Couch. What do you check on the couch? The couch is important, right? You don't want a couch to move around, to be sloppy. Some couches they retrofit a couch, like they'll get rid of the bearing couch and they'll put a different couch on there. Sometimes the screws aren't as tight as they should be. So the couches can get sloppy. We had a retrofit couch at Lutheran, and it was a couch because the old bearing couches weren't carbon fiber, or they had metal in them, and so we wanted a carbon fiber couch. We put one on, but it had these pins that would fall out all the time, and I'd see them on the floor, these pins. So the couch would be all rickety, and I'd find screws and pins on the floor, and I'd have to screw them back in. So check for that. Obviously, that's bad, right? Especially if you're doing IGRT to set up patients, and you think you got them right on, and and the patient fidgets, and the whole couch moves. Your IGRT setup is off. Okay, couch applicators, so electron applicators, make sure, again, everything's nice and tight. And then gradicule. Gradicule. We use gradicules. Who's seen the therapists use gradicules? What's a gradicule for?
For the ligand, I guess. Sometimes if the actual setup is off too much from the DR, then they're going to put a BB tray on it or something to compare the position.
Okay, so your gradicule is your origin, right? It gives you your axes and gives you little dots, little markers. Okay, but do therapists always use the gradicule? Well, first of all, the gradicule, would you use this in KV imaging or MV imaging? KV imaging?
I think it would be to line up with the bones.
Well, yeah, the gradicule I'm talking about is the hard gradicule that slides in the head of the machine.
Oh.
Okay, that's what I'm talking about. There's two gradicules. There's a hard gradicule that you could hold, and then there's a software gradicule that shows up on the screen. Okay. Now, the software gradicule you'll see on both MV and KV. You'll see it show up on the screen for both. The problem with the MV gradicule that shows up on the screen, the digital gradicule, is that you'll only see it as long as you have your field size is defined inside your imaging area. So there are situations where it's not, and that situation is when you're treating a very long field, and you'll take an MV image of that long field, and the top and bottom borders will be cut off because the imaging plate just is too small for it. Okay? In those situations, the software doesn't know where the edge of the field is, so it can't calculate the center to put the graticule on there, the software graticule. In those situations, the therapist needs to take the hard graticule that you hold and stick it in the head of the machine, and then they image with the hard graticule, and then they can see they see the dots because it shows up. Okay. So that's why in most cases you can use a software graticule, and in KV imaging it's not an issue, but in MV imaging again, if one of the field edges is off, the software can't calculate the center. It doesn't know where the center is, and then they have to go in and put the hard graticule in. So because of those situations, we need to QA the graticule, and this is something I definitely check on a monthly basis because it's off a lot. And it's off a lot because when they put it in, they slide it in, and then it hits the end. Well, the metal piece hits the end, but the little acrylic piece that drops below it, that's only screwed onto the metal piece, so it can shift a little bit. Every time they put it in, it can shift a little. So I often, almost every time, I'll see that graticule being off, so I have to adjust it almost every time. If they don't use it that often, it's not off for it. It's not off center. Okay, collimator isocentricity, crosshair centering. So that's just rotated collimator walkout. You guys have probably done that test. Gantry collimator angle digitals. Tolerance is less than a degree. And couch digitals, very long on that. You guys are all okay with all that stuff, right? You've done that? Okay. Who's done QA here? Okay. How many times?
A couple.
Couple times monthly or quarterly or yearly?
We did the annual, and before we had to do a monthly, and then after we did a monthly because like some errors came up, so we wanted to make sure it was all right.
Okay, good. Okay, so you got some errors too, which you learn better when there's errors because you know how to fix them. How have you done? How many have you done?
I've just done breaking the Accelerator QA.
Okay. Any Linac QA?
We're going to do Tomo soon, but we keep getting caught up with things last minute with these add smart flags. They come in and then plans just don't come through. So we're doing QA at 6:30 tonight.
You are? Wow. Okay. Who does the QA?
Right now.
Is there one person assigned to do all the Linac QA, or do they have one in the room? Or?
For the patient QA, it's whoever's doing it. For the annual, Derek does Wall 1. I'm not sure who does inpatient, and then Dr. Thomas does Tomo.
Okay.
But we keep getting caught up with patient QA.
Do they do some interest to patient QA?
No.
No.
They'll create the QA plan, but we actually shoot the QA.
Okay. Couch digitals along with that. So Don, you'll get practice in this when you get a chance. And that's, well, you can't really see it. That's just it's a film of light versus radiation field checker. Okay. And then here's an output from RIT. It's an older version of RIT. And so what we used to do for flatness and symmetry is we would take a film and put it on the treatment couch, irradiate it with a known field size, and then scan it in RIT. So this is transparent film, not the RTQA film. Transparent film. And we run it through the scanner, and then RIT will give us an output. So it tells us these numbers are central axis. Okay, hold on. It gives us full width half max. Here's the flatness, and look at this. It tells you where it gets the flatness formula, TG45. So that's good to see. Symmetry, TG45 equation again, and then it tells us the size of the penumbras, 5.3 right penumbra. So you can track this too. Penumbras affected by usually energy and depth where you're measuring it at. Table to gantry profile, so this is the other direction. Okay, so this is the kind of RIT output. This is really nice because it gives you a lot of information about flatness and symmetry. But this was probably done with V-film. Yeah, you can see a little writing right here. V-film, so that's that older film that you needed to process. Today, if you do this with chromic film, it's kind of expensive if you're going to do this every month. So today, people don't tend to use film for flatness and symmetry. They tend to use things more like the profiler or the IC profiler, which is an ion chamber profiler. MapCheck too, you can use MapCheck for doing flatness and symmetry. It's less expensive than running through a piece of film every month. But again, nothing wrong with using film either, and RIT. Okay, so moving to yearly tests. So these are tests that can change less often than within the year. Outputs, so you'll do a TG51 on a yearly basis. Okay, it's an IEMA requirement. It's also standard of care. Intercompare with plastic phantom per monthly. You guys remember that? We did all this together, so at least once. So you kind of remember that, right? So you do TG51, and then you intercompare with plastic to get your intercomparison factors. Okay. And one thing that you should do is, there's another requirement is that you need to check the constancy of your ion chamber. Okay. So your ion chamber can drift over time too. So how do you know if your ion chamber is drifting? It's a good way of comparing that. So you have to have some way of intercomparing your chamber with another chamber. So it's a good idea to use one chamber, like a calibrated chamber, for TG51, and then use another chamber, like what we call a field chamber, for this plastic, okay, right here. So and by using two chambers, let's just call it a monthly chamber. So by using two chambers, you're well, first of all, this calibrated chamber is only sent to the Cal Lab every 2 years. You should check your chamber intercomparison yearly. Okay, so if you send it to the Cal Lab yearly, you're done, because you're intercomparing your chamber to what they have at the Cal Lab. But if you don't send it yearly, which most people don't, you need to intercompare your chamber with something else. And that's why if you do this step right here, that intercomparison factor, as long as the intercomparison numbers are the same from year to year, that means that the two chambers match. Right? Because even if the output of the machine changes, that's not going to affect the intercomparison factor. Because the intercomparison factor is just what you measure in water divided by what you measure in plastic. If your output is 10% higher, that factor is not going to change. Okay? So that intercomparison, as long as you do the setup very carefully, that's probably going to satisfy the intercomparison chamber requirement. Another way you could do a chamber constancy is with a source. You can take a cesium source, some kind of check source, put it at a known distance, and then check the reading that you get on your chamber. Okay. Output factors, photons. So this is something else we do. We don't really expect output factors to change much, right? What do you think output factors depend on? Are they the same for all the Linacs? Output factors, let's just say SFCP. Do you think SFCP is the same for all Linacs across the board? Okay, you think SFCP is the same for the same Linac? So I've got an IX here and an IX there. Should I get the same SFCPs? I may not. I mean, the energies might not be matched, right? Because SFCP does depend slightly on energy, slightly. Not much, but it does. So the energies might not be matched, so they might be off a little bit. SFCP definitely depends on the flattening filter. Some machines, as you get smaller and smaller field size, the SFCP will change more for the smaller field sizes than the larger ones. And that has to do with the flattening filter. Okay, so yeah, you do need to check SFCP. Well, definitely between Linacs, but will SFCP change from year to year? Very highly unlikely, because that's affected by the position of the jaw. So if you're confident about your jaw's place plus your, it's not going to change SFCP. And the energy, if you're confident your energy hasn't changed. Okay, so that's not going to change much. That's why we only do it once a year. And you don't need to check every field size. You can just spot check certain ones. Okay. Electrons output factors. Again, the output factors depend on the flattening. The scattering foil, and they also depend on your cone. Okay, so if your cone is crooked or not aligned properly, your output factors. Wedge factors, those don't change much either. Okay, and they're directional, so you want to change directions and check them out. Output versus gantry angle. That could possibly change if your gantry integrity is not so good. You know, if it's not rotating around an axis. MU linearity. So MU linearity, I mentioned this before. That's the test where this is dose. You do this with a chamber. You put a chamber in phantom, and this is dose per mu, and this is mu. And then so you'll go down to like 1 mu, 2 mu, 5 mu, and then maybe 100 mu out here, and then you'll check. So dose per mu should be constant across. Okay. And remember how I said it does this kind of thing? Okay, so for low mu's, you tend to get a little bit higher mu. So you just want to just check this on a yearly basis to make sure that the linearity is there. It starts to become linear, maybe, and this isn't exactly right. It probably comes down a little deeper than that. Okay, it starts to become linear at around 4 mu. Okay. And then scanning PDDs, check your PDDs to make sure they're the same from year to year. What can affect PDD? Energy. So if your energy drifts, your PDD is going to drift. Another thing too, what I found on a machine that was overheating. You know what a chiller is? It's this thing that cools water. A lot of hospitals have them for air conditioning. And they run chilled water through the hospital. Well, we tack off that chiller and we feed the Linac with the chiller water. So the chiller water goes into Linac. Remember that water cooling system when we were talking about? So the chiller water comes in. If the chiller's down and the Linac is overheating, that can actually affect PDD. I've seen PDDs look completely wrong when the Linac was overheating. So you might spot a overheating Linac issue if your PDDs are off. Profiles. How can profiles be off? So that's your symmetry and your flatness. Flatness is very difficult to let flatness change, but your symmetry can change. Again, if your bending magnetic currents are off. Gantry, couch, isocenter, we do star shots for those, and we check those. Okay. Gantry, mechanical isocenter, front pointer. So the mechanical isocenter, the gantry, that means that the way I check that is I set up a front pointer to 100, and I put a needle. So here's my couch again. And I'll stick a needle on the end of this couch right here. And then I'll align the front pointer to the needle and I'll bring those two as close as possible at 100. Okay. And then I'll look at it from the side and then I'll start rotating the gantry. And I'll see where that front pointer ends. So what happens is that front pointer is going to start to walk away from the needle. Okay, check them out. And so there's a tolerance for that. I think it's about 1 millimeter is what the tolerance should be. So this front pointer can move in this direction as it rotates. It can move in this direction. It can move into the page. It can move out of the page. So it can walk around. So this is a good test to verify the mechanical integrity of the gantry. And that separates it from the radiation mechanical integrity. The radiation isocenter, I should say. Okay, so this is what star shots look like. So we just star shot for couch, collimator, and gantry. And then these are the different procedures that you follow. Complex jaws to 0. So this is the gantry one. We've all done these, right? Remember the gantry, you put a piece of film, close down the jaws and rotate it, and you get that pattern. Well, what do you do with that pattern? Well, one thing is you can, if this is a film, you can scan it into RIT, and RIT will give you your, it'll scan it and it'll tell you what your diameter of the circle is. And this is a zoomed up view of what's in the center, and this is what you're trying to do is you're trying to inscribe a circle inside the little triangles when you look real close. How do you get those? How do you get these lines? How do you get where do those lines come from? These red lines.
Are they just the rays?
Yeah. So if you're using RIT, it'll do it for you. But if you're using a film like RTQA, which is what I use, I take a really thin pen and I'll put a mark. I'll start on this spoke and I'll put a mark in the middle of the spoke. Well, that doesn't look like the middle. And then I'll put a mark in the middle of this spoke and I'll draw a line with a very thin pen or with a scribe, with a sharp scribe or a needle. And I'll do that for all the spokes. And then I'll look really close with a magnifying glass or a loupe. And then I'll try to measure this distance right here, this diameter through the circle. And that diameter has to be less than 2 millimeters. That's the tolerance. Okay. And modern Linacs easily pass that test. Okay, let's take a break here. Okay, let's take a break, and then we'll talk about TG142. I know this stuff is a little dry, but it's a good opportunity to go through it and just talk about it a little bit. All right, TG142. TG142, September 2009. So let's talk about what TG142 came out. So TG142 addressed new technologies. There was nothing about MLCs in TG40, nothing about asymmetric jaws, So it addressed all these new technologies, dynamic wedges, virtual wedges, portal imaging devices. They also addressed image-guided radiotherapy, such as cone beam CT, planar KV, addressed respiratory gating, addressed stereotactic radiotherapy, total body radiation, IMRT, and they also brought in this concept of baseline values. So it's an updated protocol. Now, as you can imagine, with all this new technology, what does that mean? More work, a lot more testing, which is what we do. We should be doing more testing. And so this is a guidance protocol that came out to help us test those devices. So what is TG142? What does it not do? Well, there's a few things it doesn't do. It doesn't tell you how to perform the tests. Okay? It just tells you this is an imaging system. These are that you should perform the test on this frequency, this often, and that your tolerance should be this much, 2%, 3%, whatever. It doesn't tell you how to actually do the tests. Well, where do we learn how to do these tests? How do we learn how to do them? Okay, so that's a challenge, because when 142 came out, people were like, oh, that's nice, but what do I do about this? So, let me see, where is it? So TG198 was formed to address that issue. Okay. So this is not even out yet. It's still in press, it's still in the works. TG198 is an implementation guide for TG142 QA of medical linear accelerators. Not yet available, guys. Okay. So what do we do now? It's not available. What do we do? Well, your manufacturer of the linear accelerator has typically, I don't know about Electa, but for Varian, they have a pretty detailed customer acceptance procedure of all of these systems, okay? That's what I use, and that's my best, that's what I've been using, because that's another way of comparing it to baseline. Your baseline is the results you get during acceptance testing. So if you're following a certain procedure from your manufacturer of acceptance testing, and you're writing down the results you get, at that time, you either pass it or fail it. Hopefully it all passes. Those are your baseline values. So why not use that procedure on a monthly basis or quarterly basis and compare your results to your baseline? So that's what I do. I don't do every test that they have in there because I don't find them all relevant. But what I've done is I've taken those acceptance tests and I've correlated it to TG142. And so I've tried to match them up as best I could. Okay, and then so what else does TG142 not do? There's no QA for tomotherapy or robotic radiosurgery. Okay. And I think these two TGs do address QA of tomo and robotic, so they're separate TGs. Okay. How often do you do QA on the tomo?
We have monthly and quarterly.
Quarterly? Okay. How long do they take?
I haven't actually been around for any of them yet.
Okay. How about robotic? What do you think robotic radiosurgery is?
The CyberKnife.
CyberKnife, yeah. Some people think robotic is the 60 couch, but it's cyber. Okay, so anyway, there's an implementation guide that you guys should know that it's coming out. So those are some things it doesn't do. Tolerance and action levels. This is something else that's covered. I really like this part. This is something else that's covered in TG142. And so we know we have tolerance levels. Remember that 3% for the daily QA, that's a tolerance level. 5% is another tolerance level. So there are different tolerance levels. And then, so once we hit the tolerance levels, what do we do? What do we do at that point? So say our tolerance level for the monthly QA is 2% for outputs, and we get 2.5% measuring output. What do we do? Okay, so this protocol gives us a little bit of an idea, a guidance of what we should be doing. If you ask one physicist, he says 2.5%. That's like 2%. It's close enough. If you ask another guy, no, I calibrate it right there. There'll be varying opinions on what you should do. Okay, it should be a little more standardized than that. We should all be kind of thinking the same way. So this guidance document gives us these action levels. So inspection, level 1 is inspection. Okay, inspection just means it's outside of your tolerance, but it's not, you consider it not that big a deal because it's like 2.2% or 2.5%. Not a big deal about 2%. But inspection means that you've noted it. You've noted it, and you don't necessarily have to do something about it. Okay. So that's for things that are not don't require instant action. that you need to do something about it, even though you're inspecting it. Level 2, schedule action. So level 2 would be something like you've done 2 monthly outputs, and both your outputs have shown that your, I don't know, electrons, 6 MeV electrons are off by 3% in a row. Okay, now at that point, that's when you should say, I'm going to do something about it. Okay, they're above my threshold for 2 months in a row, and I'm going to do something about it. And so you write a note, and you'll say, I will do this about it. It could be, I'm going to check it in a week to make sure it's still 3%. It could be, I'm going to calibrate it within a week. Okay, it doesn't need to be immediate. It's going to be scheduled action. Okay, schedule could be immediate too, but the immediate is really for this level 3 down here. So immediate action is something where the tolerance level is at such a point that it could affect patient's treatment, could affect patient's dose delivery, and you need to do something about it right away. Okay, an example of that, your output is 5%. If I see an output that's 5%, I'm not going to go home. I'm going to sit there and fix it until I get it to within acceptable levels. Okay, another example, you do your isocentricity walkout test, and your gantry looks completely off. You got to do something about it. What's another example? What do you think another example would be? Immediate action. Think of all the QA tests we talked about.
What about flatness and symmetry?
Okay. So what would be an immediate action tolerance level for symmetry? What's a typical tolerance for symmetry? 2%. Okay. So where would you? So if you get 2.5%, would that be level 3? Okay.
About like 5%.
Yeah, 5% would probably be a good immediate action level where you should do something about it. Okay. So you should probably call the manufacturer and say, I need you to come in here and adjust this. Now, 5% still, 5% for symmetry, and it might not be the end of the world, so you might be able to get away for a day or two with the manufacturer coming in. Sometimes they can't come in right away. Okay, so you might get away with a day or two for 5%. I would not say that for outputs if you're at 5% for outputs, because you can actually actively do something yourself. Okay, you can do that. So, so yeah, that's a good example. Another example, a wedge being loose, and you got to do immediate action. All right, so these are nice. These are nice levels. So now, I've incorporated these into my worksheets, and so now every worksheet I have in my worksheets are just a list of tests and results. And then I have a pass, I have an action level on the right for every test I do. Okay, because it's important if somebody looks at my report to not just be a bunch of numbers in my results, did it pass or not? Okay, we want to indicate that for every test. So I have an action level, I have a column on the right, and it doesn't say pass fail, and now it says action. That's my new column. And then if it's pass, I'll just say pass. Okay? And if it's inspection, I'll say level 1. Level 1. Okay? If another test is level 2, I'll say level 2, another. So I have an action column now. Okay, and then down at the bottom of the spreadsheet, I'll explain what this means. I'll say this test here, light versus radiation field, level 1, and I'll say comment, and I'll say why it's level 1. I'll say off by 2.5 millimeters on X1 job. Okay, and I'll explain that. Okay, and then that's recorded, and it's very clear. Anybody that looks at that report can see that you've explained what the issue was with that. Instead of just saying pass/fail, if you say fail there, sometimes in the past I've said fail, and then I'll look back and go, oh wait, this failed, and I didn't do anything about it. Okay, so now I have a comment section about what I will do and when I'll do it. Okay. So then when I bring it up again, I look at it and I know what. I mean, after a month goes by, especially I do so many Linacs. I can't keep track of all the Linacs, and so it reminds me about what I need to do the next time around. So, so that's a nice feature that was explained in TG142. Okay, again, sticking with the TG142 theme, baseline versus absolute. So these two terms are used a little more readily in TG142. And the goal of the QA program for Linacs is to assure that the Linac does not deviate significantly from baseline values. There's a typo. values obtained during acceptance. That's the goal. That's what you're doing when you're doing QA. You're making sure that it agrees within tolerance values of your baseline. So here's some examples of baseline comparisons. Beam flatness. Okay, so your beam flatness when you accept your machine could be 2% for a particular energy. So you could, every time you measure beam flatness, you want to compare it to that 2%. Okay, and if it changes, say it goes to 1%, that's better, right? 1% is better, but it's different than what you originally measured. Okay, so you need to look and see why it's different. I mean, flatness, I shouldn't say it's better because, I mean, we know that flatness changes, right? So at Dmax, I'm going to exaggerate the horns. At Dmax, it looks like that. At 10 cm, a little flatter. And then at 30 cm, it looks like that. Okay, you expect that to be consistent every time you measure flatness. So if you measure this is at 30 cm. If you measure your flatness when you accept the beam and it's 5%, and then the next month you get 0%, you know something's going on. That's not right. Okay? Even though it improved at 30, that's not right. Okay, so that's why we want to compare baseline. We just want to compare constancy. Another baseline, couch gantry collimator isocentricity. Of course, you want the isocentricity as ideal as possible. Okay, so it goes through the same, right? It's through the same spot. But chances are it's not going to get much better than when you accepted it. Okay, so if your isocentricity for your, you know that little circle that's inscribed inside the triangles, if that's 2 millimeters when you accept it, it's probably going to stay 2 millimeters. And you'll just want to make sure it doesn't go beyond 2 millimeters. And then what's the tolerance? So say your baseline is 2 millimeters. When you accepted it, you need to put a plus or minus something right here, right, for your tolerance for that. So you need to decide what that is. And I mean that depends on the manufacturer. So you could talk to the manufacturer about what that tolerance could be. So 2 millimeters, it probably shouldn't, just off the top of my head, it probably shouldn't deviate more than plus or minus 1.0 millimeter. Okay. Output factors. Okay, so those are actual values, SOCP. You get a number for that output factor. So those output factors can't get any better than a certain number. Okay? So your output factors should be whatever they are. Again, plus or minus something. Now, I know that output factors are pretty solid. Every year they're the same number. So I would say that I want my output factors to be plus or minus 1%. That's pretty tight, but I think that I can manage that as long as I set up everything the same way from year to year. PDDs, usually this is 1 millimeter. Right? So your PDD should be within 1 millimeter. Off-axis factors, again, this should be around 1%. I don't have the protocol up. I probably should have brought it up. But anyway, those tolerances are in the protocol. I can't remember if these are correct, but this is my expectation, what I would expect it to be. Do you have the protocol up there? Yeah, anybody have the protocol? What? TG142. Can somebody bring it up? No. Josh, when you were doing your yearly with AJ, do you remember what your tolerance for the PEDs were?
I remember it was built into the spreadsheet.
So it was built in? So it would say fail if it was off?
Yeah.
Okay. That's the problem with spreadsheets. It's too automated.
Well, I guess he wrote the spreadsheet, so he knows.
Mm-hmm. You have the table there?
Yeah.
Okay. Can you tell me what those are? What those tolerances are?
It's annual or no?
Mm-hmm. Yeah, let's go to annual.
Off-axis.
Yeah, just give me PDD first.
So PDD 1%.
1%, okay. And then
1 millimeter shift.
1 millimeter, 1%, okay. And what about output factors and stuff? I don't know what's there.
2% from baseline.
2%. I would say.
For electron applications.
Okay.
For electrons.
Okay, so anyway, and then off-axis factors, those are the that's the difference between the reading you get off axis divided by the reading you get on the central axis. And depending on the shape of the curve, those will be different between different machines, but it should stay the same within the same machine. Okay, so those are baseline values. What about absolute? When do you use absolute? So absolute would be, even though the TG142 says that beam symmetry should be baseline, I think that because it's easy to tweak your symmetry, it's easy to steer your beam, you can try to always get beam symmetry as close to 0% as possible. So, and your beam symmetry is going to, anything that you can modify, I would say would be a more absolute. Or dose prime U too. So that's what you can modify dose prime U when you do TG51 during your calibration. Okay, so that's an absolute also. So when you accept the machine, if your TG51 when you accept the machine is 1.01 CGY prime U for 6 MP photons, and you're okay with that because it's only 1%. You're not going to compare your monthlies to 1.01. You're going to compare them to 1.00. Okay, because you can always modify that to 1.0. Okay, so does that stuff make sense? All right, and so just getting into some tests here. Some tests that TG142 talked about that wasn't in 140. One of them is the MLC collimator static test. Okay, so what you want to do for this test is get a piece of graph paper, bring up. This is where you have to understand how your the software in your Linear Accelerator works. On the very machine, there's a software called the MLC Workstation that you can run. And with MLC Workstation, you can pull up MLC plans. Okay. So there's some test plans in there if you know where to find them. And one of them is a triangle test plan, and the other one's a circle. You could bring these up, and then the MLC will drive, and you'll see if you put this graph paper on the couch, you can project the light field, and you can outline where the MLCs are. So you would do this during acceptance testing. And so what you do is you align these crosshairs to the crosshair in your light field, and then it'll bring the pattern in. And so you do this on a monthly or quarterly basis. Okay, just make sure that the MLCs go to that pattern. So you can do 2 patterns, 3 patterns, whatever you want, whatever you have time for. Okay, so that's a static test. And then just keep the graph paper in the room so you can just grab it when you have to do it. Multi-leaf collimator dynamic test. So these are done in different ways. One is picket fence, which we talked about last time. Who's done a picket fence? I used to do picket fences. I stopped doing picket fences because it's just a hassle. Because I use a pore limager, and you got to move the pore limager around because it's a really big field, and then depending on how you window and level, picket fence looks differently, and it's very qualitative to me. I like quantity. I like numbers. So what I started doing is I started using the variant acceptance test procedure. So this is what we do during acceptance, is this test right here. We use a pattern that we bring up with the MLC Workstation, and it's a dynamically moving MLC pattern. And the way it works is it moves both banks of leaves, all of them together. So it stops at a certain point, and then moves them, and then stops, moves them, and stops. And so what it does as it's doing that, it's logging the positions of the leaves. Okay, so it knows where it's supposed to go, and then it records where it actually goes. So then it takes all that information of where it's supposed to go and where it actually ended up, and then it looks at the errors of every single leaf during that pattern. Okay, and then it gives you a histogram, and I'll explain what this means. These bin numbers right here are error bins. Okay, so it's looking at, and this is in centimeters. Okay, let's look at down here. This is 0.4 centimeters. So the bin that corresponds to any error during those leaf movements that occur between 4 millimeters and 4.5 millimeters, the percentage of those errors are going to be right here. Okay, so in this case, there were none. Okay, in this run. But if we reduce the distance error, and we go down to this point right here, so this is 0.5 millimeter to 1 millimeter error. Okay, well, how many of those were there? Well, 15% of the errors were in that bin. Okay, so there were some errors that were in this bin between 0.5 and 1 millimeter. Okay. And then look at, and between 0.5 millimeters and 0.05 millimeters, there's a whole bunch more. Okay? Because now we're talking about a really, really tiny error. Okay? So that's not that big a deal. And then even smaller, there's a percentage there. Now, this is the DVF. The DVF is a program that you run after the leads have marched across. You run the DVF, and you open up this log file, and it gives you this kind of information. So what's this tolerance? There's a bunch of numbers there. How do we know what passing is? Well, the passing criteria comes from the acceptance testing document invariant. And the passing criteria is right here. Greater than 95% should be in the first 8 bins. Okay, so which means that in the first 8 bins down to here, this should be greater than 95%. Okay, so the 95% of the errors should be in these bins here, and it's okay if 5% of the errors are down here, but not more than 5%. And so what does that correspond to? That corresponds to errors of 3.5 millimeters and up. Okay, so there cannot be more than 5% of the errors at greater than 3.5 millimeters. That's their criteria. And whenever I run this test, it always looks like this. I mean, it looks really good. Now, you need to do this test at a certain dose rate, and let's see, yeah, for a certain number of monometers and a certain dose rate. Because if you increase your dose rate, the leaves are going to march faster, okay, and your errors go up. So you always have to do that at a certain dose rate, a certain number of monometers. And I pushed the system where it fails miserably, but hope, and then it gives you an idea of clinically where you should be too. But what I mean by that is, if you're running the Linac Accelerator at 600 MU per minute, you'll get a different result than if you run it at 200 MU per minute. 200 MU per minute, things will pass very easily. At 600, they won't pass as easily. Okay, now let's look at comparisons between TG40 and TG142. So TG40, look at how small this table was. So the daily checks on TG40: X-ray output constancy, electron output constancy. I wonder if there it works. Electron output constancy, mechanical. So localizing lasers, the therapist check lasers, check ODI, door interlock, AV. Okay, and then look at the daily over here. So things got a little more complicated. First of all, there's 3 columns: non-IMRT, IMRT machines, and stereotactic patients. Okay, so it's not a very efficient use of space, and I said there's a lot of white spaces. But anyway, so they've split those up. X-ray output constancy for all energies, 3%. Okay, that's the 3% that we were talking about before. All right, and then mechanical. So laser localization. This is something you guys have to remember. The 2 millimeter rule that we've always used for lasers is now pretty much 1.5 centimeters. Most of our Linacs today are IMRT capable, right? So we're looking at our laser localization accuracy of 1.5 millimeters for most of our Linacs. If you're doing SRS, you need to make sure that your lasers are within a millimeter. ODI, that really hasn't changed at all. See, they're all the same. So the ODI check is the same. Collimator size indicator. So that should be your job positions. Okay. So for SRS, your job positions need to be 1 millimeter. What else? Safety. This stuff is pretty much the same. Door interlock, closing, AV. Okay, stereotactic interlocks. You guys know what those are? Stereotactic lockouts. What stereotactic lockouts are? We have them in the trilogy. I'll show them to you, Jimmy. When you're doing a stereotactic procedure, there's a panel with switches on it, and those are lockouts for all mechanical motions. So during SRS, you lock them out so that the couch can't suddenly glitch. You know, there can be like electronic noise as you're treating a patient, the couch starts moving. Okay, so that locks out all power to the couch. All right, so you got to make sure that those are working. Actually, I haven't checked that. I should check that. Make sure that those are working. Radiation area monitor, okay, and then BMOD indicator. Those are just things that have been on the room for many years. Okay, so those are some differences between 40 and 142. Okay, IGRT. Extremely important for patient setup accuracy. We now put a lot of trust in IGRT, don't we? We take pictures and we assume everything's right, but we have to check that. For MV imaging, for portal imaging, the Las Vegas Phantom. Have you guys seen the Las Vegas Phantom? Okay, Las Vegas Phantom is a piece of aluminum, and it has holes drilled to different depths along the Phantom. Okay, so there's different holes, and so these are drilled to different depths. Some are shallower, some are deeper. And you take a picture of that, and you expect to see a certain number of holes. And that's also in the Variant Customer Acceptance Procedure Manual. Okay, planar KV. Well, for planar KV, when you're doing KV shots, you need to measure your image quality. You do that with the lead spanner. You know what that is, right? You guys know what the lead spanner is? It looks like this. It's a thin round plate about this big, okay, and there's little objects in there. Okay, there's little discs in there. You see these discs, and there's more contrast in this disc than in this disc because it's thicker. Okay, there's a bigger difference between the thickness of this and the outside surrounding material. In the middle, there's what we would call a high-resolution test pattern. And so the image quality test, one of them is it up there? No. One of them is low contrast detectability. You have to be able to detect structures of low contrast, okay, like soft tissue versus dense tissue. That's what these do. Okay, so what you do is you count how many of these you can see. You count the number, record it, it has to pass within a certain tolerance. Okay. The other test is a high resolution test, and that's done with line pair tools. Every item on these are different. The distance between those lines are different. They get sharper and sharper. Okay, and that allows us to measure how good the system is for finding high contrast structures. So you count them, and they have to be above a certain number. Okay, so that's the tolerance. So that's just a simple image quality test, and then you do shift accuracy. When you do an IGRT, you're usually shifting a patient, right? You take pictures, and then the computer says you need to shift the patient this much. Of course, you haven't seen that yet. You're done. Do you do this stuff at your clinic?
I don't think we've done it. If we've done it, I haven't done it.
Oh, okay. So you're also measuring shift accuracy, and what you do for shift accuracy is you have a block that you put on the Linac table, okay, and that block has a BB in the middle of it, and so what you do is you offset that block by typically 2 cm on all 3 directions. You image it, and then you align the images during IGRT, and then the computer gives you a shift. It says, well, you need to shift this much. And hopefully that shift is the 2 cm shift that it gives you. Then you have the system shift the block, just like shifting the patient. Okay, and then you go in the room and you verify that it's on the lasers. So you're doing that too. So you're doing image quality, shift accuracy, and then image geometric accuracy. You do this one by placing what we call a circuit board. This is for the varying machine. A circuit board, and it has squares on it, metal squares. You take a picture of it, and you measure the dimension of the metal square. Okay, and that should be within a certain tolerance as well. So those are the 3 main tests you do for planar KV. CBCT, again, shift accuracy, because you're going to use CBCT for shifting. Okay, you do the same test, but now you're doing a CT scan on the machine. The image quality, you use a different kind of phantom. It's a CAT fan, and that is a cylinder. Who's seen a CAT fan? I know Jimmy's seen it. You guys seen CAT fans? It's a device that comes with the varying Linac, and it's a cylinder that you mount on the couch, and that cylinder has different sections in it. And inside this, I'm not even going to bother drawing it. Inside the section, there are tools. Actually, one of them looks like this. There's a high-resolution test tool for CT, and there's another tool that looks like a low contrast detectability test tool. So you're basically running through the same steps, but now you're doing a CT scan with a different kind of phantom. So you're doing high contrast resolution, low contrast detectability, uniformity. That's when you look at your CT scan after you do your CBCT, and you ensure that you pick 5 regions of interest in an even area. There's an even area where there's no structures. There's just even solid water material. And you make sure that the deviation between these 5 areas is within a certain limit. The range is within a certain limit of CT number. Okay, within those 5 areas. So that's uniformity. And then dose measurement. We also, I haven't done it until recently, but you can measure CTDI. CTDI stands for CT dose index. Okay. CT dose index it's a measure of dose that the patient would get if they have a CT scan. Okay, there's a formula for that. So there's something else you should measure, and you can measure this and compare it to published values. So that's for typical test for CBCT. Okay, TG100. So TG142 is a lot like TG40. Okay, in that, okay, there's more tests, but you're still doing the same thing. You're doing the test, you're comparing to a tolerance. What's wrong with it? There's a problem with that, because we're just doing these tests just because we could do the tests. Now, current QA paradigm may not make the best use of our time. Okay, remember how I moved some of my tests to quarterly? Okay, because I know that some of those tests don't change much, so I moved them to quarterly. Well, this is what TG100 wants to do in a much more detailed and much more scientific and statistical way. TG100, by the way, it's not out yet. So we've been working on this for years. TG100 wants to implement statistical data to determine which tests should be done more often based on risk assessment. Okay. Now, I use my statistical data that's in my head, and I move things to quarterly just because I know, anecdotally, that things don't change. Well, what they're doing is TG100, they're compiling statistical data about how often something breaks down. And so what they want to do, the idea is to specify certain tests that should be done more often based on statistics. So they also want to do process mapping. And what's process mapping? So process mapping could be, you want to do the IMRT process mapping. Very simply put, a process map is a step-by-step procedure of what you're doing. Number one, scan patient. Okay, scan patient. Number two, plan. Okay. Number three, do QA on phantom. Okay, et cetera, all the steps that you follow for an MRT patient. And then, in those steps, you're going to insert where errors can happen. Okay, scan patient. And then under scan patient, you'll say, patient's orientation not sent correctly, patient not scanned from top to bottom. You're going to find all the possible errors that can happen in each of those steps. You're going to put that in your map. Same thing here, front. You're going to find all the possible errors. These maps get really complicated. Okay, so that's process mapping. Now, TG100 is going to take care of that. You guys don't have to do it. Okay, failure mode and effect analysis. I don't know too much about this, but the FMEA, you'll see the acronym a lot. FMEA, failure mode and effect analysis. Okay, so what that means is that how can something fail, and when something does fail, what effect does that have? So they're looking at that. They're looking for all of those process maps. They're looking at the FMEA. What would be the cause of a failure? You know, if you scan a patient and the wrong orientation comes in, what effect does that have? Fault tree analysis. Actually, fault tree analysis was the second part of that, looking for faults in those trees. Establishment of risk-based QM program. So now we're assigning risks to all of those steps. How risky is each of those errors? And then, so they've called this RPN. They've come up with this risk priority number, and we want to minimize this risk priority number. So this is where it gets a little more quantitative. So the risk priority number is equal to O times S times D. Okay. Now, O is the probability that a cause will result in a failure. Okay, so what's the probability that if an effect occurs at a certain point in there, what's the probability that that will result in a failure? Okay. So if we say the patient's scanned in the wrong position, what's the probability that that will cause a failure? I mean, that would definitely, it's pretty high, okay, for that case. Other cases might not be so high. Okay, severity of effects if not detected. What is the severity of a patient being scanned backwards if it's not detected? Okay, obviously, if the patient's gone backwards, then we might be treating on the wrong side of the patient. Okay, very severe in that case. I've chosen the worst case. And then D, probability of failure not detected. What's the probability of nobody picking that up? Okay, so they're going to assign probabilities to all of these based on all the fault tree analysis and based on the process mapping. So someday we'll have this protocol, and it'll give us these risk assessments. Okay, now the higher the risk, obviously the more often you want to test something. So that's TG100. Okay, CT Sim QA. All right, so now we're changing gears. I've got an old-fashioned sim. You guys ever seen one of those?
Yeah, they had one in Kentucky.
They did? Really?
Yes, and they use it for emergency patients.
Oh, okay. Yeah, it's quick and dirty. This is the one, this is, I don't know, I got this one. But this is a variant Symmetron. We used it for many years at Lutheran. It was in where the HDR unit is now. I used to live in there, the simulator.
Involved from the
In the inpatient, yeah. That's where it was for many years, yeah.
Okay.
Until they decommissioned it. So I just put that picture up just so you guys look at it, see what an old one is. But anyway, ours, today's CT simulators all look like that. Obviously, it's a CT sim. And this comes, the CT Sim QA, there's a completely other different guidance document to it, and that's TG66. And this is the kind of stuff you do on a CT Sim QA. And honestly, at Evanston, we have to be a little better with this because we don't check it that often. CT number accuracy, again, for this, you're going to use the cheese phantom. Remember the cheese phantom? Okay, so you're going to use the cheese phantom. Not on a daily basis, but more on a maybe monthly or quarterly basis. But on a daily basis, our therapists definitely measure the CT number every day for water, and that has to be within 5 Hounsfield units. It never fails. I mean, our CT scanners are pretty good. So on a monthly basis, you use the cheese phantom, or you can use the cat fan, because the cat fan has different materials in it. Image noise, the therapists definitely measure image noise, and image noise is basically you put an ROI in an even area of the phantom. And by the way, these phantoms are watertight. They put an ROI in there and they look at the standard deviation. The standard deviation is how much those Hounsfield units change within a certain area. And that has to be within a certain number. In plane, spatial integrity. So what you could do is you could scan a phantom of known distances and then take the measure tool and make sure that they're correct. Field uniformity. Monthly, most commonly used could be annual. Okay, so field uniformity I already talked about. It's those 5 regions that the Hounsfield units have to be within a certain range, and here's the range right there. Okay, CT to ED, again, that's the cheese phantom. Okay, spatial resolution, that's the high. This is only done annually, and this one's done annually. These are already talked about. Those are those two test tools. Nope, this is the one with the line pairs. And then this is the one with the circles. Okay. So this is basically what we should be doing at minimum. Okay. Oh, here's a picture of an image uniformity. Here's a scan through the water phantom. And so an image uniformity, a lot of CT scanners, you just click on a uniformity test, and it pops these 5 circles on there. And then what you're seeing here is X and Y. It's the position of the center of the circle. The mean CT number is right there, 3.87, and there's the standard deviation. Okay, so let's see, in this case, we've got 3.87, 2.45, 0.99, 3.4, and 2.83. Are those within 5 Hounsfield units? Yeah, okay, so they pass. So the therapists do this every day on a CT scanner. Virtual simulator. Okay, so a virtual simulator, what is a virtual simulator? A virtual simulator is after the patient's been CT scanned, the CTs are sent over, and now we can put beams on the patient. It's not really treatment planning, it's simulation, which means you're going to put beams on there, and the software is going to let you look at beams I've used so the doctor can, well, first, obviously, they're going to contour the tumor and contour ORIs on the virtual sim. And then they can put beams on there and look at the beams I've used and adjust their field size, okay, to whatever they drew. They can adjust their blocks to whatever they did. They can move their isocenter around. So basically, that's pretty much all a virtual simulator does. Okay? And it generates DRR so you can see it. So those also have to be verified. It has to be QA, that software. And many places will have a virtual sim, and will also have a treatment planning computer. Some places will not have a virtual sim. The doctor goes straight to the treatment planning computer and does everything there. Okay, but if there's a virtual sim that's separate, like we have at Evanston, we've got to do QA. And we do QA. Well, one way of doing this is, oh, by the way, I gave a talk at the 2010 APM. This is the link right here. It's they recorded it, so it's on the APM website. You have to log in, though. If you paste this, you'll hear my talk. This was in Philadelphia in 2010. So I go into gory detail about virtual. I'm not going to tell you everything I talked about in the talk. But one thing you could do is you could scan this. This is a circuit board that comes with variant Linac, and you could put little markers on here. You scan it, and then in a virtual sim, you'll place a beam at the isocenter, and then you make sure that those markers that are right here line up to the grid. Okay. So that's just a geometric test that you can do. And that's it. I thought this was a cool slide. Okay, we covered a lot of stuff. Of course, we didn't cover all aspects of QA. I didn't cover HDR. I didn't cover dynamic wedges. There's a lot that I didn't cover, but we did a lot. I'll let you guys look into the rest of it. So I think we covered the basics. Any questions? Go out there and do it. Doug, you got to get some practice, man. Push your guys up there.
I've seen lots of patient-specific QA, just not so much the monthly